Hello, I'm gonna talk about polarcode today. Here is the content I'm gonna talk about. So first, I'm gonna give an introduction to polarcode. The polarcodes was firstly described by Dr. Erdo Erkan in 2009. He is a Turkish scientist. In information theory, polar code is a linear block error correcting code. It has modest encoding and decoding complexity. When the code block length is n, the complexity of both is n log n. It is the only method known can achieve the Shannon limit theoretically. And the kernel idea of polar code is channel polarization theory. And here are some effects I think should be kept in mind because I think it will be helpful to understand the polar code. The first one is polar code is based on channel polarization, and the channel polarization is based on channel combining and channel splitting. And the polarized channels are not physically existent. We use a math method to extract the individual property of each channel. And so the base knowledge we need to know, the first one, is if we are given a binary discrete memoryless channel, x is input and y is output, p of y given x is the transition probability, and x can only be 0 or 1 with half probability for each. For channel W, we have two main parameters of this channel. The first one is the channel capacity, which we have already learned in the class. And the second one is Bhattacharya parameters, and the definition of these two is here. So the channel capacity IW is the highest rate at which reliable communication is possible across W using the equal input. It is a measure of rate. It is also called the symmetric capacity. And ZW is an upper bound on the probability of maximum a posterior decision error when W is used only once to transmit a single bit. It is a measure of reliability. So here's the property. When IW is approximately equal to 1, ZW is equal to 0. And when ZW is approximately equal to 1, IW is equal to 0. And the second base knowledge we need to know is the Kronecker product. The form of Kronecker product is as shown in the figure. And that if we are given two matrices, the dimension of A is m by n, and dimension of B is p by q, then the dimension of the Kronecker product of A and B is np by nq. Here's an example, and there's something we need to notice that if we switch the position of A and B, let's say we calculate the Kronecker product of B and A, usually we will not get us the same answer. And here is an important property of Kronecker product, which we are going to use for the later content. So channel polarization, as shown in the picture, the channel polarization includes channel combining and channel splitting. It is a transformation that one combines n independent binary discrete memoryless channels and get a union Wn through linear transformation. And then we split it into n corresponding channels W and I. After the process, some channels will have channel capacity convergent to 1 and the others will convergent to 0, while n becomes large enough. Here we have the definition of channel combining. It is that we use a recursive way to combine n independent W's, make it a channel union Wn. It has a group meaning. So maybe we should give an example. Here we have two channel W's, and the input of the first channel is U1 plus U2 mod 2, and input of the second channel is U2. And we can write the mutual information of these two channels. 2IW is actually equals to the mutual information between X1, X2, and Y1, Y2. And it's also equals to U1, U2, and Y1, Y2. And use the chain rule, we can actually get this second equation. And we notice that U1, U2 is independent, so we can write it as the third equation. And now we observe these two terms. We can actually regard the first one as this, as we regard this as the channel with the input as U1 and output as Y1, Y2. And the second term, we can regard it as the channel with input U2 and the output Y1, Y2, U1. And the first channel is called W minus, the second channel is called W plus. And the mutual information, we actually have in equation IW minus is less than IW and IW is less than IW plus. So here's a question. Are these channel reals? The answer is yes. So we suppose W is a binary erasure channel and the erasure probability is P. So for W minus, we have the output Y1, Y2, and which may have these four conditions. So we observe it. The first one is useful, and the second one, third one, and last one is useless. So we can get the erasure probability of W minus. The P minus is 2P minus P squared. And similarly, for the channel W plus, we have output Y1, Y2, U1. And it may has these four conditions with their probability. So we observe it. The first one, the second one, and the third one is useful. And the last one is useless. So the erasure probability of W plus is P squared. And we know that P as a property is in the range of 0 to 1. And we can get that the P plus is always less or equal to the P minus, which means that if we have less erasure probability, we can get more certainty of the output. And we will duplicate these two channels. We duplicate W minus and we duplicate W plus. So we can get 4 channels and their input and their output, and we keep doing this for many times. we get a general way of channel combining as shown in the figure. The combining is a recursive procedure, and each time we turn n independent channels into n half-channel groups, and recursively, through log n steps, we get the combination of n channels, and the probability transition formula is given as this one. So the left-hand side of this formula is easy. We can see the union as a single channel, and the input is U1n, and the output is a vector Y1n. But what should we interpret about the right-hand side about this formula? So we take an example. If n is equal to 2 and if n is equal to 4, we actually can get this. So we have the right hand side is actually we are doing a multiplication calculation, but we also need to consider that we have done the linear transformation in the input. So every round we have input vector u1n, and we make s2i minus 1 is equal to u2i minus 1 plus u2i mod 2, and s2i equals to u2i. So basically the construction before we used. And Rn is a permutation matrix, maps this vector v1 to vn to v1, v3, v5, and blah blah blah, v2, v4. So basically it places the elements with odd indices first, and then the elements with even indices. So after the channel combining, we have channel Wn, and then we are going to split it into n channels WnI. And the method to split the channel is assume we have a decoding process. We fix the order of decoding, and if we have U1 to Ui minus 1, and it is decoded correctly, so we can actually have this transition probability defined as this one. But if we use this one to do the decoding, it is actually exponential complexity. So we need to simplify it. We can rewrite into the recursive way. So if we write in this way, it is actually makes the decoding in a linear complexity. So after the channel combination and the channel splitting, the channels will be polarized. Here is the channel polarization theorem. And actually I did an experiment on MATLAB to see what can we get. Here is the experiment. So here's the code, and we click run. So here I choose the big N is equal to power of 2, power 10 of 2. So we can see that some of the channels have the channel capacity as 0, and some of them have the channel capacity as 1. Here is an obvious phenomenon of polarization. If I increase the block length, if I increase the block length n, we can get even more obvious polarization here. Now we have the steps to produce polar codes. The first one is we need to measure the reliability. So if the channel is binary ratio channel, we actually have the Bhattacharya parameter. We can calculate as this. If we get the parameter smaller, the corresponding channel capacity is bigger, vice versa. So if it's not a binary ratio channel, we can actually not get accurate Bhattacharya parameters. But we can use other methods. Dr. Erican actually gave a method named Monte Carlo, but its complexity is exponential, so it's not useful. And there are many other methods. Some are called density evolution. Some are called there are many methods here, but not unique. So the second steps we are going to take is the bits mixture. We choose the most reliable K-splitted channel to transmit the bits, and the rest of them is gonna transmit the frozen bits is usually 0. So then we get the original input vector u1m. Then we need to construct a generation matrix. Here we got two figures. It is from the paper of Dr. Erican. Dr. Erican said that these two construction of the generation matrix of the channel combining is actually equal. So the generation matrix we get according these two figures. This one is actually we get this from the first picture, and this one we actually get this from the second picture. So here's my proof that these two Gn is actually equal. The proof is based on the property of Kroneck product and the property of permutation matrix. It is easy. And then we need to get the generation matrix. The final expression of the generation matrix is this one. Gn is equal to Bn times the Kroneck product power of F. So here, the Bn is the bits reverse order process matrix. Well, what does that mean? It means that if we have, let's say, if we have a vector and we write the indices of the every element in a binary form, and then we switch the first bit and the last bit and the second bit and the last two bits of the indices of each indices. And then if we want to construct a polar code, we need 4 parameters. And the polar code is right, I forgot to mention. The polar code is also called the GN coset code. So we need 4 parameters. The first one, n, is the code block length n. It must be a number of the power of 2. It is very important because If we do not have n as the power of 2, we cannot construct as what we design. And we have A. The A is the subset of 1, 2 to the n. It is the indices that we choose based on the Bhattacharya parameter. We choose those channels to transmit the message bits. And the K is the dimension of A. And UA complementary, it is the frozen bits vector we actually are going to transmit. Usually it's just all 0 vectors. Thank you.
So, hello everybody. We're gonna do an example of a polar code. So, let's just stick this off the pen. Okay. Let's assume that the code block length of the polar code N, the big N, is 8, and the bits we are trying to transmit, the K, is 4. So we list every formula we need to use. First is the linear transformation formula. Gn equals to Bf. Okay, so let's assume the third parameter A is also what we choose, the channel we want to transmit the bits, the index of A. The index in A actually is 4, 6, 7, 8. So the complementary of A is 1, 2, 3, 5. And we assume that the frozen bit is 0. And the message we want to transmit is actually 1. Okay, so now for the bit mixture we get 0, 0, 0, 1, 0, 1, 1, 1. That's the original input mix, the message vector we get. Okay, now we need to get the generation matrix. And we know that the generation matrix is actually can be written as this, the simplest way to write the GM. And we can do this in MATLAB. And in MATLAB, there are two functions we need to use. The first one is we need to calculate the Kroneck product. In MATLAB, we write this as this. A is the first parameter and B is the second parameter. It is equal to this. And it will return the Kronecker parameter. And then for Bn, we know that Bn is a function that's actually doing the bit reverse. What does it mean? So let's take an example. If we have a vector, the elements in this vector is 1, 2, 3, 4, 5, 6, 7, 8. Okay, and now the indices of every element is, if we write in binary form, is actually 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0. So what does Bn do? The function Bn is actually doing this. He put the first 0, he switched the position of the first bit and the last bit. So this one becomes this. This one became this. And we rewrite it in decimal. And we rewrite, if we do Bn, let's say this is x. If we do this, we actually can get 1, 5, 3, 7, 2, 6, 4, 8. This is what we got. So back to the generation matrix, we got the power of Kronecker product, this one, and then we can also do this in MATLAB. The function is called bit rev order. We get this into function and we will do the bit reversal process. And I entered the matrix and parameter into MATLAB. Now I'm writing the generation matrix. What I got from the MATLAB is 8 by 8. So we got this generation matrix. And further, we got the generation matrix, and what should we do? We need the final step is we need to get the polar code. So the polar code, we write this as C18. Okay, so C18 is to use the mixture bits we actually get from here, U18, 0, 0, 0, 1, 0, 1, 1, 1, 2. So we actually get 0, 1, 1, 0, 1, 0, 0, 1. So this is the final polar code we actually get. Thank you.
Hello. Yeah, the reason I choose polar code as my project topic is because the first one is because at the start of this semester I want to choose the coding theory class, but unfortunately we don't have this class, so it is kind of atonement for me. And second one, I start to know polar codes. It's because of the news that Huawei announced that it has win. It has they won the competition of the standard for 5G, and they use the polar code as the 5G control channel standard, and the LDBC code for the corresponding data channel. Yeah, it is quite interesting. Yeah, because of 5G. So before I didn't cover the decoding of the polar code. It's because I'm still learning on that. I know there are SC algorithm and SCL decoding algorithm. Basically, when we look at the channel combining and the channel splitting, they are kind of similar process for the generation of polar codes and the encoding of polar codes and the decoding of polar codes. So, but that's not the only question about polar code. Before, I also mentioned that if it is not a BEC channel, when it comes to the other channels, the Bhattacharya parameter may not be accurate. So there are many other methods to determine the Bhattacharya parameter, like density evolution and the Monte Carlo algorithm, etc. So yes, there are many open questions for polar codes, and I'm kind of interested in the coding theory, so I intend to keep studying on it.